Alright, welcome back. We're going to talk about a few manipulations of inequalities today and conclude with the triangle inequality, which is a very important inequality in analysis. It allows us to show things are big or show things are small, more often small, while we're manipulating quantities or trying to show a limit exists or continuity exists, or we're trying to take a derivative, that sort of thing. So the first thing I want to start with is the inequality that if x squared in absolute value is bigger than the absolute value of y squared, then absolute value of x is bigger than absolute value of y. Okay. And the converse of that, if absolute value of x is bigger than the absolute value of y, then absolute value of x squared is bigger than the absolute value of y squared. Okay. I've got two if statements here, and they're converses of each other. One starts with a hypothesis and gets a conclusion. The other one starts with that conclusion that we had before and gets the hypothesis of the first statement. When we have something that looks like this, these two statements are called equivalent, and we use the term if and only if to go between the two hypotheses. So I'm going to rewrite this as an if and only if statement. So absolute value of x squared is bigger than absolute value of y squared if and only if the absolute value of x is bigger than the absolute value of y. Okay, this statement is an equivalence statement. Two things are equivalent because if one happens, the other one definitely happens, and if the second one had happened, the first one had definitely happened as well. So you can't separate them at all. You can't find some situation where one of the statements is true and the other statement is false. They're either always both true or always both false, so they're equivalent. So let's prove this, and we're not going to quite prove this statement as it's written. We're going to manipulate it a little bit, and to do that we're going to start by subtracting y squared from both sides. We'll start with this left hand side, and I get that x squared is bigger than absolute value of y squared if and only if absolute value of x squared minus the absolute value of y squared is bigger than 0. Right, if you take away the same quantity from both sides, then the inequality stays the same. And this is true if and only if, well, this is a difference of squares, we're just going to factor it. So you get x in absolute value plus y in absolute value times x in absolute value minus y in absolute value is bigger than 0. So we factored that. Now I've got the product of two things, and it's bigger than 0, and this side's definitely bigger than 0 because it's the sum of two positive things, right? We don't know about this one yet, but this guy is definitely bigger than 0. So this is true. I multiply by something positive and get something bigger than 0. The second thing had to be bigger than 0. So x minus y in absolute values each is bigger than 0. And on each step of this manipulation, I could go back and forth, right? If I start with something positive and I multiply by something positive, it stays positive. I've got the factored form, I distribute, and I end up with this, manipulate, and I get there. So we can go back and forth. We can go this way, the backwards way, or the forwards way, and this is proven that if and only if statement. Okay, so there's just a simple manipulation of inequalities. Something like this would be something you might do when you're trying to find limits of functions or continuity of functions in the future of the course. Okay, now let's go with the triangle inequality. Okay, this is easy to state. The triangle inequality states for any two numbers, x and y, that are real, absolute value of x plus the absolute value of y is bigger than or equal to the absolute value of x plus the absolute value of y. I said any two real numbers. That's fine. If we think of these as their magnitudes, their distances from 0, this holds in any good system of measure. So if I was going to measure the distance between any two objects in some other way besides just straight line distance, I would definitely want this triangle inequality to hold. This is an axiom for what we call metric spaces. And axioms are kind of what defines something. So a metric is how you measure something. If we have a set of objects and we have a metric on them, we're able to determine the distance between any two objects, or the difference between them. The measurement, the metric in that space, is the difference between the two objects. And this inequality holds in any metric space. It's an axiom for metrics. So we want this to hold no matter what the metric space is. Some really common examples of metric spaces are the real numbers. We can measure the difference between any two real numbers. Complex numbers, we can measure the difference between any two complex numbers. It's the modulus of the difference. The magnitude of a vector is a metric. We can use the taxicab metric in R2, which isn't straight line distance, it's the distance that you would have to travel from here to here if this was sort of gridded out. The taxicab metric is how many horizontal distances and how many vertical distances added together. And that metric is also a metric, and the triangle inequality holds in this metric. This is the Manhattan metric. So why is it called the triangle inequality? Well, I said it worked on vectors too, so let's look at vectors for just a second. Let's take a vector x, starts at 0 and gets to this point right here. So there's x. And then on to x I'm going to add y. So let's say y does this. So this is y as a vector. So I go from 0 to x to y. Then this vector right here would be x plus y, right? And I've got this triangle. What this says is the magnitude of x, or the length you would have to go along the x vector, plus the length that you have to go along the y vector, is farther than or bigger than the length that you would have to go to get to x plus y together if you had gone in a straight line. So there's that triangle. It's the x, y, x plus y triangle. So okay. So let's just prove this with real numbers first. I'll probably have you prove it with two-dimensional vectors on a homework assignment or an exam. So let's start with the proof of the triangle inequality. To do this, we're just going to start with the absolute value of x plus y. We're going to square it, and we're going to end up with we're going to start with the absolute value of x plus the absolute value of y. We'll square that, and we will end up with absolute value of x squared plus 2 times the absolute value of x times the absolute value of y plus the absolute value of y squared, right? Now I'm going to put an inequality in here, this side, so this guy right here, he's bigger than or equal to x squared. I don't even need the absolute values on x squared because in real numbers x squared and the absolute value of x squared are the same thing. And this middle statement, this is positive for sure, right? So I'm adding something up here. If I take away those absolute values, I get a possible bigger than or equal to 2xy, right? This term here could be positive or negative. We don't know. Up here we added, here we could add, so I would have equality, or I could have subtracted, so I'd get the inequality, and then I have the y squared there, which is exactly the same. Okay, and then we get another equal statement. Well, I can just factor this. This is x plus y squared, right? Which is equal to absolute value of x plus y squared. Okay, so now I have the statement that x plus y and absolute value each squared is bigger than or equal to absolute value of x plus y squared. Now let's refer back to our proof earlier. If I have two real numbers, if the squareds are bigger, then the things that weren't squared were bigger. Okay. And that's the proof of the triangle inequality. Alright. This inequality comes up everywhere. We just did it with real numbers. We have it for vectors too. I'll probably have you do the proof for vectors as an exercise.